First of all, on behalf of iStar, I would like to welcome everyone on this platform and thanks to Dr. Sanjeev Gupta for accepting our invitations to present his research work. As we know that this is the iStar monthly online lecture series, and every month we had a lectures on different topic of the aerosol research. So this is the 15th lecture on this series. Instead of this, we also organize a workshop, conferences, and training schools. So in this regard, at end of this month, ISTA is going to organize a aerosol workshop on aerosol instrumentations at IITM Pune. So this workshop will provide a good golden opportunity for the students and early career researchers on hands-on for the model instruments. So I encourage all the students and early researchers to register soon, as the deadline is approaching very soon, probably 10th of this month. In addition to this, we are also going to organize a conference, iStar 2024, which is going to be held at Doon University in the month of December, third week of this year. So this will provide a good platform. So, and ISTA is known for a good scientific discussion where different types of aerosol research is discussed on a single platforms. So I request everyone to register and share your research findings at this conference events. So now I am going to ask to Chapra ma'am to introduce our speaker, Dr. Sanjeev Gupta. Ma'am, it's over to you.
Thank you, Dr. Shani. First of all, it is really a pleasure for me to see that ISTA has been organizing this monthly lecture series, and for the last almost, as we said just now, it's the 15th talk that we are having. So 15 months of continuous lecture series, which is a very good thing. And also, it is a great pleasure for me today to be here and introduce Dr. Sanjeev Gupta, because we have had some interaction in the past, and since we have been doing similar kind of work, it is always nice to follow up his work, and we are happy that today he is here to address a very different and niche area in the field of nuclear aerosols. So, just to give you a brief introduction of Dr. Sanjeev Gupta, right now he holds the post of the Deputy General Manager and Head of Reactor Safety and Engineering Division at Becker Technologies in Germany. He has his PhD in fluid mechanics from France, and he joined Becker Technologies in 2008 as head of the experimental program. Before joining Becker Technologies, he has worked with the French Alternative Energies and Atomic Energy Commission and also at the Paul Scherrer Institute in Switzerland on large-scale experimental test facilities in the field of hydrogen safety and nuclear safety research. The current focus of his work is on severe reactor accident research in LWR, light water reactors, with particular focus on combustion risk and source term issues. So his current work responsibilities, they include the development and management of international R&D and industry projects. He's also the program manager for the ongoing International Joint Nuclear Safety Project, OECD NEA Themis, and he's actively involved in NEA writing activities and also in task forces as working group on analysis and management of accident as a member. Dr. Gupta is also coordinating the ongoing international in-kind project IPRESCA related to source term research. He's the advisory board member of the ongoing EC projects on combustible gas risk management and on some others related to small modular reactors. And he's actively involved in the IEA activities as an expert and lecturer. So with that introduction, we all look forward to hearing from Dr. Sanjeev Gupta in this very important area. So over to you, Dr. Sanjeev.
Thank you, Dr. Safar. Thank you very much for the kind introduction. And I really appreciate the invitation from ISTA, because this is a good opportunity for us also to share what we are doing in Europe here and to learn from each other. So with that, I think I can share my slides, and please tell me if you see it, and I will put it in the, so now it should be in the PowerPoint mode.
Yes, we can see the slides.
Yes, Okay, perfect. So thanks again. And it is really a pleasure for me to talk about the nuclear aerosol research. And I will talk through some aspect what we are doing here. And maybe this can also pave the ways for the, let's say, future orientation of potential cooperation. So these are the just the contents of my presentation. So I will talk after introduction why we need the aerosol safety research. I will very briefly, because before I go to the containment, just a few words on the release from fuel and on the reactor containment system. So I will put focus on the water cooled reactor, but let's say touch, and then main focus would be on containment with some experimental analytical research. Then I will, what we already discussed about, I will put some examples of the activities, what I thought could be of interest with my intention that there is a more participation from the Indian organizations there. And I will talk about some future activities, and then I will end my presentation with conclusions and perspectives. Okay, so means I think it is very important to first put it into the context. When we are talking about nuclear. So, for example, if I put in the view graph from OECD NEA, and there are two scenarios where we are talking about, let's say, the conservative approach, where we see the long-term operation of the existing reactor. And also when we talk about the more, let's say, the ambitious projections with the SMRs, and I think everyone knows there are right now more than, I think, 80 designs. And in Europe, we are talking 4 or 5 here. But if this is considered, then for sure, this shows the good contribution of the nuclear component to achieve the goal of this 1.5 degree centigrade scenario. And in that context, I think nuclear plays a very important role. So means for sure, LTO and SMRs are important. But we should not forget about the safety aspect, because whenever something happens, I think uh, there is a more talk about the negative side than like we hear from the past, only few large accidents, but very widespread, let's say, the coverage and long time coverage, I will say. And on the aspect of safety, I think we saw that what happened in Fukushima with the hydrogen explosions, and then with the release of radioactive materials, including the cesium, iodine, and other isotopes. And this did the contamination not of only on the air side, but also the water. And the water, I think they were talking about the leaching of the degraded fuel that continued long time. What I put in on the right side, the issue is not only the what is happening source term wise within the reactor, but now in Fukushima, they are discovering even some specific metallic aerosols containing cesium more than 400 kilometers away. So here, I think what was deposited on land and by the resuspension and in atmosphere, this is still, let's say, transported quite far. So one has to really consider this aerosols to understand really under the broad spectrum of scenarios. And that's why I will put into context uh, all fission products are important, and aerosol has a very specific importance in that context. And that brings to the source term. So on this slide, when we talk about source term from a containment on from a reactor, I think this is very complicated. So here, like we talked about little bit, chemistry is involved. And as chemistry is involved over time, I think we have to really capture the evolution. And this evolution is within the reactor is also complex. So that's why I put it this figure. So we had a specific workshop on source term by OECD NEA, and I was presenting there. And then we talked about all these aspects in this workshop as well. So here we have to really look into the specific boundary conditions, because when we are talking in containment, we have to connect it back to the other part of the reactor, that what was originated, why we are considering in containment like that. And this is what we saw. So that in vessel release to the reactor containment, to the containment, and through containment, then due to leaks, like controlled or uncontrolled release, like controlled can be through the FCVS, containment venting system, and through the leaks. And all this plays a role to know what was in gas-borne state when we did, for example, FCVS action. What could be the potential that what type of aerosols are there? If these are large aerosols deposited, everything is nice. But if it is gas-borne, then as soon as you do the venting, all this is available to go to the vent, and then vent depends on the efficiency and also the chemical characterization. And here the word remobilization is really coming back and back into discussion. And and then apart from this in-vessel scenarios, there is also when RPB is broken, and then we are talking ex-vessel scenarios, and also some containment by scenarios like SGTR, steam generator tube rupture, and the main steam line break. And all these scenarios has to be investigated so that the courts have the specific data for validation. And for that, for sure, we need the codes, but we need also the validated codes. And for that, we need the qualified experimental infrastructure. And I think one experimental facility will not serve the purpose. And because everyone talk about extrapolation, scaling, and for that, I think there has to be a combination. And that's why here is coming the if there is a experiment done in the multiple facilities on the same phenomena, for sure on the scaling aspect, they provide the good insights. So here I put in some let's say main things for the different parts like fuel. I think when we talk about fuel and fission product chemistry, irradiation also plays a role. But this is chemistry. So chemistry we can do in the small scale facilities because there we have to only talk about chemistry aspects. But as soon as we go to the distribution or like in the containment, as it is up to 70,000 cubic meter in PWRs, there we need the small to technical scale. Or means larger scale is better, but one has to also consider the financial constraint because large doesn't mean that you can measure with the same accuracy as you are doing at the lab scale. So this is the big challenge there. But what you can study, I think this is important. Whether all the phenomena, those are of importance, could be studied there. So that's why I said also the interaction with what is available, like decontamination paint, different type of aerosol, water pools, and also the interaction with the safety system. Because when there is a severe accident management aspect, how does it has interaction on both aspects? So this has to be also studied, including some events like hydrogen combustion. What can happen to aerosols? Because combustion means high temperature, and high temperature means the chemistry might change. So all this, and there are several facilities here I also mentioned, and maybe I will show you few examples. So for example, here you see the facilities from CEA, from Verdun facility in France, and they are doing the fuel release experiments. Means you need very high temperatures, up to 1200 degrees centigrade. And then they go to the RCS, so you are decreasing the temperature up to 700 degrees centigrade. So means you are cooling down. So this release and transport loops, they can study there. Then there are some facilities at IRSN in France for the chemistry aspects. So they can really study the chemistry, even with the irradiation. What I don't have here, EpiQ facility there exists. There are in Finland facilities, and they are doing really the, even ruthenium is a topic here, and iodine, and including the irradiation part. So this can be done there. I am very happy also, and this was my pleasure when I was there in 2016 to learn about very impressive facility. Those existed, like nuclear aerosol test facility, and with the containment part. Also, what is important, and this topic is, I think everyone knows about, is storm facility, for example, that existed before, and those studied also in the pipes. And this deposition and resuspension behavior is still, let's say, I will say, a topic of interest, maybe considering different scenarios. And this is really for the core validation data, a good very example. So I put in some very interesting papers what I saw, and maybe for persons who are not involved, I think, or not have seen that, I think, even for me, this was very interesting to quickly go through it. And this was where I was present in Kanpur, IIT Kanpur. And as I remember, this was originally built for PHWR reactor experiments. And in the pipes, resuspension behavior, what was very interesting also to see this hygroscopic aerosols and the charge effect. So these are, let's say, the experiment, those can be good for the submodels, I will say, to really see the effect of charging. And also that is a growth experiment. So I will give you some example, but these facilities, I think, are doing great job, I will say, considering the data. And maybe in the international fora, this has to be bring more into intensively what type of data they are, and how is that temporal and spatial resolution, but they can be very interesting. Uh, then, for sure, I will put the facility what my organization is operating, and this is called the Thai facility. And we are covering several topics there related to containment, but we can also cover the RCS experiment by installing some auxiliary hardware. So means we have worked with the pressure difference of up to, let's say, 40 or 50 bar. So we can install the external vessel and then study the thing. So it is a large vessel facility, design pressure 14 bar, 180, and we can work with real hydrogen in this facility, 80 cubic meter, multi-compartment, and different type of aerosols. So means cesium, silver, tin oxide, and we have our own aerosol generators for that purpose. And it is also licensed to use the radio tracer for the iodine measurements. And we also, since Fukushima, we also started to work with the carbon monoxide because this was an issue after the Fukushima experiment. So on the aerosol research aspect, I had put, let's say, this all the four subsections what I showed, like fuel. So means we are talking about in-vessel, and leaching is also an issue. There are some European project recently launched to talk about the liquid phase iodine chemistry, because this is also becoming very important. In the RCS, then we have the distribution behavior in containment, and then the aerosol mitigation system, like the venting or pool scrubbing. Pool scrubbing can happen whenever there is a water pool there. So from the fuel release side, there have been very, I will say, extensive research. And what I am presenting here, this is done in the Verdun and Vercours facilities in France. And then they were able to categorize the different type of aerosols. And this is important, I think, when we are doing the experiment to connect it back, what type of species we are considering. So this volatile, semi-volatile releases, low volatile, but this is the release from fuel. So means what is released being, when it will reach to the RCS, this might again, let's say, have certain influence. But there are a lot of data, and what is interesting here, for example, in case of some non-volatile or low volatile species, like coming from the cladding like tin. So if you see that tin in aerosol or in the environment, it really shows the indication that there has been a fuel degradation. And there is a lot of experiment also using the tin oxide then. So this is, let's say, that the background that keeps what type of different aerosols are can be released from the different. Once they reach to the reactor containment system, then we are talking about, let's say, in the pipes, large diameter pipes. But then there is not only a high temperature, because in the RCS we start in LWRs around 700 degree, but also the gas composition is changing. This can be oxidating conditions or reducing conditions. When there is no oxygen, more hydrogen. And this, what has been also seen, that this has a very strong impact. So not only temperature, but the gas composition. So for example, increasing concentration of oxygen has shown the formation of gaseous iodine. And similar thing has been observed for cesium molybdate aerosol formation, or when there is a, let's say, hydrogen, then this can be present. So I think this effect of gas composition is very important to be considered on the aerosol behavior there. So now I come to the aerosol behavior in containment. So here I think we are talking about several hundred kilograms of aerosols coming from fission product, but also the structural material. So this can be, let's say, the inactive aerosols like tin, different type of insoluble and aerosoluble, different particle size, and multi-component. So means when we are doing experiment, I think this is also a challenge, because code people, or when we talk with the modelers, they want to see the real conditions. Real conditions means multi-component. But to produce a multi-component aerosol is a challenge. You can produce a aerosol mixture, but multi-component would be really by evaporation. I think this has been done in some experiment. But this let's say really to have at the large concentration there. This is then in a large facilities is a challenge there. But also aerosol behavior. So means here I think natural aerosol processes, those will have an influence, like the particle growth and the deposition on surfaces. Then also the transport by gas and liquid flows and decay heat for sure. And then the engineered safety features like the filters or sprays. So I see that there is a lot of experimental work also on the spray side, and this might have an impact. So all these processes, I think they will have a strong impact on the aerosol behavior in containment. And here I put in a list of the important topics. Those have been subjected to the research. So this was, let's say, a state-of-the-art report published in 2009. And what you see, the list of topics here, I will not go through one by one, but you see that these are the topics, those have been covered in the past. Charge effect, I think in India, there have been a lot of work I saw. And we are talking more remobilization behavior. And right now, this is what I want to put in. There is a more and more focus coming on this revolatilization, like the temperature conditions or resuspension when the aerosols have been deposited. And due to any reason, like due to combustion or due to turbulent flow, they can resuspend. Resuspend means the final particles again in containment. So this is are the really recently ongoing discussion there. So before I go a little bit more on detail, I think important is to see when the aerosols are coming and there is a certain thermal hydraulics, like the humidity effect, this plays a role. And this topic was covered, I think this is the KEVA program that was done by our preceding organization. So Becker Technologies was before called Batel. And at that time, there was another facility that was KEVA. This was a Indian standard problem also based on this experiment. And there was studying, let's say, different type of aerosol. Those are representative for the severe accident. And they were generated by evaporation, single and multi-compartment, and they were studied in the different type of thermal hydraulic conditions there. So what was interesting to see there that if you see all the 3D view graph, I think what you can only main highlight was that the hygroscopicity of the aerosols plays a very important role. So whatever aerosol type you have, if there is a more hygroscopic aerosol, this will take over the let's say the behavior of this mixture. And that's why this hygroscopic aerosol like cesium, for example, they are very important to be studied. And on that topic, I was happy to see the work done in India and what Mr. Joshi had sent me on the bark activities. Several papers are there on the humidity effect, on the hygroscopicity, how the growth of this hygroscopic aerosols can happen under humidity ranging from 35 to 90 degrees centigrade. And they have been very, let's say, accurately measured. So these are the good data for the code validation, because these are very, even the resolution wise, I think for the validation purpose, they're good. And what is also important, they provide very important insight, not only about the alone cesium iodine aerosol, but if there are multi-species like cesium iodine and cesium hydroxide, then how the settling behavior is changing. So this is really interesting to for the validation purpose, I will say, could be the useful database there. And we are happy if aerosols settle down, if they are becoming larger, because then they will be a sink somewhere in the water or in the sump. But for sure, they can come back again if the sump is boiling or gas released through the sump. But at least they are settling. So now, if you see, there is a more and more discussion to let's say investigate all the processes those can release the fine particles. Fine particles here mean the particles in the submicron range, and this is a real challenge from the experimental side, because to measure the submicron particles in a concentration very low, but also important is to really study the different processes. So here, for example, these fine particles can be challenging for the filters, because as soon as we talk about this filter gap, then we are talking about really that these fine particles can be challenging to be retained by the venting even. And there are certain processes, those are coming more and more discussion, like radiolytic oxidation of iodine. This will form by radiolytic oxidation gaseous I2 to iodine oxide aerosols. And these iodine oxide aerosols are in the nanometer range, very fine, 40 to 80 nanometers. And then we are talking about the remobilization due to combustion. This is again challenging. This will break up the particles due to high turbulence and high temperature, and also the release from the water pools. This is what is called pool scrubbing. And from large water pool in containment, what will come out, this would be also very fine. So this is, I will say, more and more, just I put in what we are discussing more. I will not go through in all the, but what I wanted to highlight here, what type of different topics are being covered. So here, as I have more access to Thai data, I took what is available from our facility. And here you see all the different OECD project, but we also have the national project running since 2000. And there is a variety of experiment, those cover different type of, let's say, processes and phenomena here. Even, let's say, starting from the distribution, deposition, reentrainment, resuspension behavior, and also the interaction with safety systems like spray and recombiner. So what I want to do here, I will not, due to time, is I will for sure would be happy to provide you more references afterwards, but I will just take few examples to show how we have done and what could be the use for these experimental data, or how it is being used. So for example, when the aerosols are coming into the containment, there is also gaseous iodine. And there is a multiple aerosol, but we cannot cover, let's say, this multi-component aerosol, because it is difficult to analyze also the effect. Because if there is a too much mixture or too much complexity, and you can also separate the effect. And that's why modelers ask us how the I2 is depleting from the atmosphere, not with surfaces. Surface is a different story, with paint, with steel, but only with aerosols. And then we said, okay, we take the bounding cases. We take one time the inert aerosol, so forget the chemistry, just the deposition on gas-bound particles. And one time we take the real active aerosol, like silver. And then we do this experiment to show how the iodine is depleting by aerosol, not by surfaces, just by aerosol. And these experiments then we are done by extensive instrumentation. And here you see the main results here. So means in the nutshell, what you can say, tin oxide is inert, and but it is gas bound. And in let's say conclusion, what we could cover, that this tin oxide also capture iodine. This is physics option. This is not chemistry option, but it is same effect like it is on steel. So if it is sitting on steel, it is taking from the gas atmosphere. So it is a sink. And in that experiment, there was no steam. So there was no steam effect here. We wanted to see just the effect on the aerosol. And when we had silver, you see on the lower curve here, then there was a really injected, and then, so here you see, this is the phase, what you see the long term until 20 hour. This is simply the deposition on surface steel. Then we inject aerosol, and this is the aerosol effect, what you see. So this is tin oxide effect, and here you see really the silver effect. Yeah. So silver effect, you see, this is really what is by the silver is depositing. So this was then the data then used really for the code validation, and the GRS, for example, they use this data, and this has been extensively used these days. So I come one step forward. So I say, okay, we looked on the surfaces, we have several data. So that's why I did not show here paint, steel, then aerosol. Then comes the processes by which we are forming aerosol. So I said one process is by radiolytic oxidation of gaseous iodine. So by radiolytic oxidation, you form the iodine oxides. And this iodine oxide is aerosol and very fine. And then modelers wanted to see how these very fine aerosols interact with the nuclear aerosols like silver, cesium iodine, different type. Then we did for this purpose experiment, and where we wanted to see the depletion of iodine oxide nanoparticles. So we formed the IOX by injecting gaseous I2 together with ozone. So, and then IOX was formed. And then we injected the different, this aerosol, we used the silver here, and then we studied the behavior. And one issue was this iodine oxide can convert back to I2 due to two mechanisms. One mechanism is the irradiation. By irradiation, you can convert back iodine oxide into I2. This effect was studied by some OECD project in France. So they showed some effect. And second effect is by temperature. So as soon as you reach temperature higher than around 80 to 100 degrees centigrade, you can again convert IOX to I2. So I think these all processes, what can form and what can again convert, becomes important, let's say, for the modeling process, so that they can consider all these reaction mechanisms and validate it for their purpose. So I think this experiment we did recently in our ongoing OECD NEA Themis project, and that's why you don't see the real data, but these data will be published also. Then there was, I mentioned that we are happy when the particles are settling and depositing, but there are processes like turbulence or like any energetic event that can again resuspend this aerosol. And for that, we studied both gaseous iodine. So first we let the gaseous iodine depositing on the paint. And here you see that this figure like one fresh, this is the fresh paint, and this is the after the hydrogen combustion, burnt paint. And this showed certain, let's say, release of organic iodine formation by the paint, and also the paint degradation, so formation of very fine particles. So I think this is for the safety purpose very important, because these particles then remain gas bound. And one experiment, what we did with aerosol, that is called here SD46, here we installed some gratings. Gratings, what you see here in the small box, these are like the obstructions, and this will accelerate the hydrogen flame, so more turbulence. And this can resuspend what has been deposited in the containment. And there we studied also what can be resuspended, and by the hydrogen combustion, and how much will be. So this is what we, the deflagration experiment, and the issue is that we really see the very, very fine particles in the gas atmosphere there. And this like the in containment source term there. So then the other type of experiment from the gas atmosphere, I don't know whether time-wise how I am doing. If someone can help me, if it is okay to, or miss, or how much time I should have more.
You can continue, please.
You have, sir.
Okay, so no, so I should not worry about it, because I am always stressed when I have to keep the time. Okay, thank you. So I have just coming to the half part, and here from the gas atmosphere, now I am going to the water pool interaction. And
Yeah, so it looks like slides are not moving, Dr. Sanjeev. I don't know whether it is the problem from our end.
now you see.
For us, the slide title is Behavior of Iodine Oxides.
No, it's moving.
No, I
It's
think
moving.
it is moving. Manish,
Okay.
Moving, Manish.
slides are moving fine. Probably it
These
is
are
right.
aerosols. They should move.
Actually,
Yeah, right out in water pool hydrodynamics.
No,
Okay.
slides are moving, sir.
Okay.
Please go ahead.
Okay.
Yeah.
Perfect. Thank you. Okay. So from gas, now we come to the water interaction. So aerosols, when they are in the containment, then they see also water. And here, this is the big issue, such a big issue that we also launched a specific project on that topic, water interaction, pool scrubbing. So pool scrubbing, here we cover two topics. So one is the pool scrubbing means the absorption of radioactive particles and vapors in water pool, means the retention in simple word. And another phenomena or process we look, it is a reentrainment. Reentrainment means, so I think we have this very nice sketches here done by my colleagues in other projects. So here you see pool scrubbing means the particles are coming with the gas. And reentrainment is that particles were sitting, then came the gas, and also they can go out with gas. They can go out also due to boiling. So no gas just by boiling. So what was the sink? This is again becoming the source. And another process is by venting. So for example, when you do the venting, and if this venting, as an example, if it is from the suppression pool, this can also boil water due to depressurization. And this can also reentrain. So when our European colleagues were involved in the Fukushima analysis, this was, I think I will have one slide on that. This was a lot of uncertainties that because Fukushima was a specific accident because this lasted several days. So normally in the CV accident before Fukushima, we used to see the process, let's say 72 hours or something. Before we used to talk in hours, now we are talking the calculations and the phenomena in days. So like this delayed releases, this word what is coming more and more into use. And so these are the two processes. And here challenge was, if you look, I put three examples. When we talk about, for example, Sparcher or BWR types, because in the Kandua PHWR, I think there is a lot of water. So I think this is not this can contain there. But in terms of the boundary conditions, from downcomer, you will have the big bubbles. Sparger can have very small bubbles, low velocity, high velocity. Then you have the venting system, very high velocity is there. So it is the jet regime called. If you go to MCCI, there is no jet. It is just by the non-condensable gases releasing. So how to cover all these scenarios into the experiment? For which scenario we are doing the experiment? I think this was the real discussion. It is still going on, and there is a specific activity I will show you on that to talk about boundary conditions for pool scrubbing, just for that topic, and covering the all different type of reactors and the processes, because there is also what I not mentioned here, SGTR, steam generator tube rupture. So if a tube that rupture 20 millimeter, the velocities are very high. So it is really a jet ingestion regime. Then we are talking also the pressurizer scenario. So I think this is really very strong topic. And after Fukushima, it got much emphasis considering this what I wanted to show you. So this I took. There was sorry, this is a type BISA project benchmark of the Fukushima accident, and it was in the frame of OECD NEA. And I put in what was in the report on the release of what the cesium was found in the water, retained was in water. So, and this is the different codes. So I think we don't have to just look very detailed. What I wanted to show you, just see the wide spectrum, what the codes are predicting differently. And then when there was more and more analysis, there were different point of uncertainties were identified. So people were, let's say, using the different accident scenarios, timing of accident progression. Important issue was also thermal stratification in pressure suppression pool. If you use a lump parameter code with one node, I think you cannot see the thermal stratification. So there were a lot of data experiment required to validate and how to, let's say, the model this suppression pool with more than one node. And also the fission product remuneration behavior. So if you see on the, what I took is the pool scrubbing or retention, this was less than 10% for the Kyrie experiment, this is here, and 75% retention in IRSN. So very wide range. And this broad discussion, here we are not talking about modeling. Here we are talking about just the codes, how they are taking the scenarios and the boundary conditions, and just by that, this effect. And now, if you go further on the modeling, I took an example. This is a Spark code, and this Spark code is also, this was originally developed in US, and Spark V was the version that was modified in Germany. Sorry, excuse me. And this was done actually my colleague, Dr. Fisher at Becker Technologies. And here you see this is just a calculation of the Spark. This is also implemented in Aztec, in Mapu for pool scrubbing. This is a module. And what I wanted to show you, there are the different experimental data here, what you see, more than 81 experiments and measured, and the calculation by Spark. For the low decontamination factor, so means when I talk about decontamination factor of 100, I am talking about efficiency of more than 99%. But if I go to 1000, DF, decontamination factor, means the mass in divided by mass out from a pool. This is relevant also when we talk about some scenarios like venting, wet venting, which has the pool also. And there, as you go higher in the DF, uncertainties is really high. And this can be relevant also for the severe accident management at the end. And also, if you are, let's say, underestimating, this means that the release in the containment gas atmosphere, it is also not, let's say, accurate. It means if you want to assess the performance of the safety system like recombiner or spray, then the behavior is different also, because you don't know what could be the uncertainty from this water pool. So I think this brought in a lot of validation work. And then what I can say, the most important, let's say, the actions has been in some organizations like in France, they are doing from scratch, checking all the empirical correlations in this code, improving them, bringing more modeling insight, more validation. So this, and not only the, let's say, the experimental data for what was also the missing was that the high jet or the high velocity regime or just churn turbulent regime. And there, no data were there, because what was developed, it was based on the very simplified experiment. Everything was done at the ambient conditions. And now, then people are asking more the representative data. So this is, let's say, after Fukushima, a lot of discuss. And that's why we had to do several experiments. And several experiment means what I want to show you, that you see some release like air injection. This is the Weber number, what we are non-dimensional number using for different flow regimes. But what I wanted to show you, on the right-hand top side, you see two sketch. One is the air and ambient. And this is what you see, what I will say idealized sketch, what you see in the model. The large bubble, break up, small bubble, and then it goes up. But if you put it, not only air, but air steam mixture, and here with pressure, we went up to the 3 bar and high temperature. These are not the spherical bubbles. the assumptions of a spherical bubble is not true, or at least then it is required that what would be the uncertainties due to these deviations. And this is also true when there were no data for the high velocity jet regime injection. So there were a lot of experiment are being done. Research. This is an example of Thai, but I can say you that also in several Asian countries like in China, Korea, in Europe, more and more are coming. One important issue was also that so far all experiment had been done with pure water. But in the severe accident, we are talking about impurities, and impurities can have an influence on the, let's say, the surfactant effect, like the viscosity, surface tension, and this will affect the bubble dynamics. And aerosols are really driven by the hydrodynamics behavior. And so this would be very important how this hydrodynamics is changing under thermal hydraulics and chemical boundary conditions. And here challenge is what are the representative chemical boundary conditions, how to choose them. And that's why as I start, there was a European project called BASM. They did some experiment, and in Thai we did, where we want to see a controlled variation in the water chemistry. Like here we put in a chemical that will reduce the surface tension by 50% compared to the pure water. And then how it changed the let's say, effect, making the different bubbles, and the effect on the aerosol release then was studied. So here just I wanted to show you, this is the one example. So in nutshell, what I want to say, when we are talking pool scrubbing means aerosol release from water pool, important is not to only put more focus on aerosol measurement, but also to measure the hydrodynamics behavior of water pool. So both has to go together. So this is very important. And this is what we did, for example, here in this experiment, what we did on pool scrubbing, and we had for the BWR scenarios. And here we installed then the optical cameras here for the bubble measurement. And then we measured the bubble diameters, and we measured the different decontamination factor under different conditions there. So these are then the data, those are being used for the code validation purpose there. This was the pool scrubbing, means where the aerosols are coming together with the gas and being released. Another is the reentrainment. So what I mentioned that here we say that there are pre-existing aerosols in the water pool, and now we study what are the processes that they can be released. So either due to continuous heat up or due to depressurization. So here we did also experiment. So here we studied by heat up, means this we do by steam release. So we heat up the pool until the boiling comes. And also we can do the let's say, the containment typical venting rates to see the depressurization induced boiling. And both of these aspects were covered in this experiment. And we studied then the cesium iodine aerosol here, and there were two experiments actually. So I am not talking here about the gaseous iodine because my focus is on the aerosols, but several experiments we do, once aerosol and once gaseous iodine, to see the effect of particulate and gaseous things there. And here you see that when we reduce the surface tension, and then this we measure the bubble dynamics, then we has the really the higher release rate of the aerosols into the containment atmosphere. And another thing was that when we had this surfactant, and then the particles what are being released, these are really the fine particles here. We are talking in the really in the submicron range there. So, and this data then we provided and people use it. Even the IRSN used it to assess the long-term release scenario in Fukushima. But I think this was the retrainment rate was not very, very high, but the important was that it can remain long time. So this was the more important insight, because retrainment factor, if I say it was 10 to the power minus 5 or minus 4, so not very important if you look the absolute value. But if you look that it can happen over a long time, this is important. I put one example when we talk about safety systems and when we are talking about aerosols in containment, important aspect is how they will interact with the safety system. What can happen? Because like I took here, we have several experiments on spray, but here I took this because this was a very focus after Fukushima hydrogen recombiner. So hydrogen recombiner are the passive system. As soon as they see hydrogen, they start up because they have a catalyst, and then the temperature increase. This brings the chimney effect, and then the flow is a natural flow here, and the power is operating. But in containment, this gas also contains the aerosols. And what happens when these aerosols are passing through, and there are different scenarios. One scenario is that when the power is not very hot, and then this aerosol particles can sit on the catalyst plates. Then what can happen? So here, that's why I said hot catalyst and cold catalyst. Cold catalyst scenarios, there we really intentionally made it before the operational stage, so not very hot temperature. This allows aerosol particle to sit, and these aerosols were very aggressive aerosols, so lithium nitrate. And this is very hygroscopic and really sit on the surfaces there. And so in this scenario, we allow to sit aerosols. So here you see the part deposits. But when we start the hydrogen, so real hydrogen, the catalyst performance was starting because we saw this was only the local deposits. So it was not really influencing the whole catalyst activity. But another scenario where we had the hot catalyst, so this was we used really a high concentration, around 4 grams per cubic meter. And there we saw that due to high temperature, means in the range of 900 degrees centigrade, you can do the thermal decomposition of cesium iodine to gaseous I2. So this release was like in the up to 3%. So it depends on how much cesium iodine you have in terms of the absolute mass. So out of that, 3% was measured in this experiment. So, and now such experiment we are doing in the recent with the other type of aerosols as well. Like the one experiment we did recently, this was with the iodine oxide and also with the fire aerosols together with the recombiner in the containment. So really a complex experiment. Okay, so I am coming to the last section of my presentation, and here I wanted to share with you some aerosol related international activities and projects. Those could be of interest. So for example, when I talked about pool scrubbing and release behavior from water pool, here really the issue was the numerical database of the major boundary conditions, considering different geometry, different scenarios, what to take for the analysis. And this activity is run under the Nuclear Energy Agency, WGAMA. So this is not a project. This is simply activity. If India is a member, you participate there. You show interest and you can participate. So here you have to share only if you have the reactor analysis. So these are we are looking for the scenarios, and this is the synthesis report is ongoing. So this activity is almost close to end now. So I am coordinating together with the colleague from CMAT Spain. And here you see the different participants. So for example, there are different chapters, there are different co-leads. What I can share you that if India has a member representative in WGAMA of NEA, this report will be released soon, but after that, this will be also publicly available. But this may take some time, up to 1 year. But to WGAMA, this can be accessible immediately. Another project is ongoing. This is on the CNOT project. This is a European project, and this is called Severe Accident Research and Knowledge Management, and coordinated by CMAT in Spain. And we are the work package lead there, Becker Technologies. So I am coordinating their one work package on the experimental database. So here, what would be very, very important to share with you, because in this project, we are developing the complete data map of the validation data for all type of scenarios in severe accident. So we are looking what kind of data are available. So there, I think it would be interesting to see what type of other complementary activities are being done. So the idea would be here, or what we are doing, to develop a PERT on CV accident, complete PERT. So here we are not talking about PERT on RCS, PERT on RPV, PERT on containment, but for a complete scenario. So this is a ongoing task. And then we develop the validation database, not a physical data, but only the relational data for the complete reactor there. And this project is right now halfway, and at the end there would be the PERT and including also the SM. So this is very important project. IPRESCA project, Dr. Supra mentioned about that I am coordinating this. This is the in-kind project. So again, here we are, let's say this started after Fukushima, and because this is focused really on the pool scrubbing. So this is, you see the research activity related to pool scrubbing. And we cover experiment, we cover modeling, and we have strong focus on measurement techniques. So really to talk about, so here you see the different type of, so I am coordinating this project on behalf of Becker Technologies. Then we have different work package and led by all the international experts. So here like from CMAT, Luis Herranz. Then we have different facility here, IRSN as a code developer is leading. And so idea is that what is produced here in this project, this is used by the code developers. And that's why we really want to involve the code developers. So GRS, for example, is involved also for reactor application, and Japan is involved strongly, Canada is involved, and we have all this project unofficially started in 2014, officially in 2018. We completed 2 phases, and now we are talking about the phase 3 to involve more SMRs. So here just I put in what has been done. So there are several publications you can find in the literature. If you have some specific interest, please don't hesitate to contact me, and I would be happy to provide you more information. And also this project involved the code benchmarking. So not only the experiment, but also the code benchmarking thing. So this is what I mentioned. So now we are talking about the future extension. And so this will involve continuation of our pool scrubbing validation database metrics. Then we will also extend the experimental database, benchmarking, and our aim is also to produce a PERT on pool scrubbing and also involve more focus on SMR. And here I am in discussion with our Canadian colleagues because there is a lot of activities in Canada involving BWRX 300 there. The last slide, I wanted to show you another related project. This is the OECD NEA THEMIS follow-up project. So right now I mentioned that this is run by my organization, Becker Technologies. And in this project, we are talking about, so at Becker, we are extending our Thai facility with our SMR facility. So this vessel would be 60 bar, submerged water cooled type, like the new scale or Nuber design. And here then we are developing the different topics here. You see this involved the thermal hydraulics, SMR specific, combustion specific, but again, a lot of emphasis on aerosols. And this would be, here you see the partners who have shown the interest so far already. So around 10 or 11 countries. And we are also in discussion with other countries. And this project might start in mid-25. So here, if from India side, organizations are interested, I would be very happy to share more information, more detailed on experimental program, and might be what can be the contribution also what exists in India on that aspect there. So with that, I come to the conclusion of my presentation. That means when we talk about aerosol research, important aspect is that we were looking until now on the lump parameter, but we see really an increased focus of the computational fluid dynamics CFD codes. And we have to also now consider experimental wise the high tempo resolution or spatial resolution so that they are the suitable data also for the CFD codes. And in the IPRESCA project, we saw these applications and we are providing data on that. And also the performance testing of engineered safety systems. This is important. when we are looking the aerosol research there. Measurement technique is a big issue. What I can share with you, I was happy to hear in the starting of this webinar that there is some plan workshop. So I really welcome this initiative. What I can share with you, we organized recently in the frame of OECD NEA an international workshop on the instrumentation that was called SWINT 2024. I was the let's say, chair for the CVXN part and lead from the W Gamma side. And this was a big success because here we discussed about application of measurement techniques, uh, not only in the experiment, but to the reactor scale and about the different type of data application of artificial intelligence and machine learning, how to use this different type of measurement technique. So if you are interested, I would be very happy to share more about this SWINT workshop that was in June, actually organized in Germany. And this can provide really the good database. Also, we are talking about more for the code benchmark. And now we are looking also seeing more and more reorientation, future experimental research, considering this long-term operation of the existing plants, involving also the upcoming light water reactor SMRs. This is in our domain, what we are working on both sides. So with that, I put in some more references here for if you are interested, and for sure, I would be very happy to share more information and exchange more on the talk, what I talk about. And I would like to really thank you for your attention and for your time. So I would be very happy if there are some question or some discussion there. Thank you.
Thank you, sir, for presenting this insightful presentation discussing various aspects of nuclear aerosols. We will now move on to question and answer session. But before taking questions from the audience, I would like to have ask some questions with respect to iodine. So the first question is with respect to the database. So like before Phoebus, the cesium iodide percentage accepted was like 95%, and remaining hydrogen iodide and gaseous iodide approximately 5%. So after Phoebus, there has been a lot of experimentation with respect to the radiolysis and organic iodine. So is there any consensus on the current status of like what is expected after an accident? Like a range, like what percentage of iodine oxide is expected?
Yeah, thank you for this question. I can follow your question linked to Phoebus. I think this was in US in these so-called world reports. This was 5% for iodine and 95% for CSI. For the moment, discussion was there, and Phoebus shows that it was not only the cesium iodine, but could be also cesium molybdate species. So means from the modeling side, what I say that people are still using the same ratio, but now what is more important when we are talking about the volatile fraction of iodine, there is a more and more focus on the speciation. So one should not look only the elemental iodine, one should also look at HOI, for example. How much, because only challenge is analysis are showing that there is might be HOI there, for example, not in addition to I2. But experimentally, it is challenging to measure HOI. It is very reactive. It converts very quickly back to I2. So there is a certain efforts there. So in nutshell, what I can say, people did not change what was the basis. This still remains the same, but with more focus on the speciation. So you should look really the speciation.
So there is no like range for the iodine oxide per se. Like how much iodine oxide will be expected after accident scenario?
Iodine oxide, actually, we are talking about, this depends, for example, there are different processes right now. So there was no calculation that shows the integral amount. But let's say by irradiation, you can convert some iodine to IOX, and by the thermal effect. So I think in the total, up to like 5 to 10% was in discussion for the moment. That can be available in the late phase there. And then this can have the certain impact back on the total I2 gaseous source.
Okay, thank you, sir. So my second question is with respect to the experimental part. So the dealing of iodine for the experiment is very difficult, like it is very corrosive. And I have read the Thai reports that they have used the SMPS for the measurement. And also the toxicity of iodine oxide is all like, it's not very clear. The corrosivity. So how did you measure the measurement part? Like, didn't it affect the SMPS? Could you
Yes.
use it afterwards? So the measurement difficulty for iodine. So how did the Thai facility handle that?
Yeah, I think this is a very good question. I can follow you. Means measuring iodine is not easy. We make our life difficult and easy both. How we do that? Because generally people use the let's say elemental iodine by injecting, let's say, in several grams, if not kilogram amount, and then measuring by the classical like ICP MS and such kind of classical technique. In our case, what we have that we use the radio tracer. So it is a tracer. We inject only 1 gram iodine in 80 cubic meter. 1 gram, only 1 gram. And this is the help of the radio tracer that allows us to measure very, very small concentration. So this is the one aspect to measure, but I did not answer until now. When we measure, for example, the issue of IOX particle measurement or how much iodine oxide is forming, this require different type of even, first, it is very small concentration, so how to take it. Second, how to differentiate. For that, we use the so-called technique that is called gas scrubber. It means we have a certain sampling station inside the vessel. We suck in the gas inside this small flask. Those are filled with some chemical. So for iodine oxide, for example, we normally use sodium thiosulfate for I2, but for IOX purpose, we use the potassium iodide. And we can then measure it, and then we can do the radio tracer measurement by NAI detector. So by that, we can measure. And then we are using also SMPS, but in combination with CPC, that's condensate particulate counter. And this we use then to measure also the submicron particles, because submicron particles you cannot measure by filter, for example, because they will not be captured there. And for that, we use the CNC SMPS.
So this iodine didn't damage the SMPS, like the CPC is optical based instrument. So iodine.
Normally, what we do, for example, for iodine, we don't retain it. We have a charcoal filter, and then at the same time, it is being released to atmosphere. But I think that that time frame is not so large that sometimes you see the corrosion in the sampling line, for sure. But it is not affecting really the electronics. Because it is diluted. It is diluted. The gas atmosphere is really diluted by the dilution before it goes to the CNC. So it is a very, very small concentration before it reaches to the measurement sensor.
Okay, thank you so much for your answers. So now anybody from the audience, the floor is open for the questions.
Yes, actually here Amit Kumar. So I have a couple of questions.
Sure.
It is again maybe the continuation of what Mariam has asked. When iodine has been iodine along with the particulates, aerosol, is suspended in a chamber, then how much fraction of iodine will absorb by particle and how much fraction is deposited in the surface? How we can distinguish by the some instruments technique what fraction will be in aerosol surface deposited and other part will be in remain elemental form, or it is not deposited with the aerosol particle?
Yeah. Thank you, Dr. Amit. I think this is a Good question and very challenging. Luckily, I had one sketch to show it. So means in the gas atmosphere, this is both form are available. Means what we avoid, we never use where you have the same iodine molecule in aerosol as well as in gaseous form. This we avoid because this is a cross sensitivity. So when we want to measure I2 with aerosol, we don't use the iodine compound of aerosol at that time. Due to that, we are, for example, here you see that we are using silver or tin oxide together with I2. And
Yes.
now we have to also differentiate what is coming with aerosol and what is in the gas phase. And what
Yes.
we do, so here you see the first line in the experiment that we have, for example, we measure what I mentioned to Mariam question. We have some gas flask inside the vessel. This like what you see like GS abbreviation. This is the gas scrubber. These are the small flasks filled with liquid, and they capture the gas atmosphere from the vessel. Then what we do, we have around 6 or 7 gas scrubbers. Then we have like in this experiment, you see the 2 gas scrubbers we have with a pre-filter. So pre-filter means this will retain the aerosol part and will allow only the I2 part. And the others we leave open. So then we measure the total I2. And then by the post-processing and analysis, then we can, comparing these 2 type of measurement, we can say what came with the aerosols together and what was really the gaseous form. So we have to install then the pre-filters in some of the gas systems.
Okay. And this regarding pool scrubbing, aerosol under pool scrubbing. So most of the experiment has been carried out in the water, whether it is a liquid water or in some high temperature of water. So whether it will affect if we change the coolant, like in place of liquid metallic coolant if we used, then because the aerosol generation will be the same maybe the gas to particle conversion while it is releasing from the fuel matrix to the pool. So how it will be challenging if we change the liquid?
Okay.
Yes. Yes.
Okay, so yeah, I think this is what I see here means what we discussed. When you say, let's say, instead of water, take other coolant there, and how it will change. This what I mentioned, like in one experiment, that in our case also in water, when we talk about chemical boundary conditions, what I see the most effect, this would be how the pool hydrodynamics will differ. Like if you put the other coolant, whether your hydrodynamics, like the surface tension, bubble formation, I will say, let's say in the simple form, how
Yes.
the bubble formations might be different due to the different coolant, due to the surface tension or viscosity, whatever effect it is. And I think this would be then important. This is okay, means whether it is water or something, but how this bubble hydrodynamics is differing together with the aerosol, I think this would be very important to know. So one has to do then maybe with the different coolant, some pure hydrodynamic experiment to compare it with, let's say, what type of bubble dynamics you see there. For example, for pool scrubbing, what we say important is what you see near the surface. So there is a release location, then there is a water pool, but this is a breakup and everything, and then near water pool, you see certain bubbles there. And what type of bubbles they are. And because you have the different coolant, maybe different surface tension, then your conversion from bubble to droplet might be different there. And this would be important. And there are very small amount of experiment even for the water, that how the droplet disintegration is happening. So this would be the important subject, that how different coolant and what is the droplet disintegration behavior at the water pool surface there. So this can define really the pool scrubbing process there.
And I have one last question. This is regarding charging, because in reactor environment always there is a bipolar ionizing field is there. So I come across a lot of literature, even though India, from IIT Kanpur, BRC, and even IGGAR also, we have did a scale down, or we can call a lab scale experiment for the charging, how the aerosol dynamics change under the bipolar ionic field. But in actual scenario, the radiation field will be very much in magnitudes of higher, and along with the other factors like thermal hydraulics. So this actually this lab scale information, how it can be translated to the like our reactor containments phenomena.
I mean, I think in your question, you also answered some part of this question, and I can follow you. I will say this is a very challenging issue. Means whenever there is a charging, this was a topic for sure. And for the moment, what I can say, when we want to discuss the reactor application, people start to discuss then beta and gamma radiation, very high dose, and how to compare this effect. What and there are no experiment actually to confirm what I can say to really with the gamma radiation or how it is changing. But what I have seen that how we use this lab scale experiment on the charge, I think for the model validation, because if charging to some agglomeration, for example, if cores are, but this agglomeration, like you said already, there might be other processes, those may play more dominant role than like the steam, for example. But for me, this more looks like the validation of the submodels, and this plays a role also for the experimental part, because if you learn about the charging, you learn about the injection procedure. Because if you say my primary particle size was 4.7 micron, but due to electrical charging, you might be generating some other type of particle size. So I think for me, this for the moment, this looks more to support your fundamental understanding. But in the reactor scale, I think you have to really consider the decay rate effect and then see what is the overall effect there.
Okay. And then recently I come across some literature where generally it is a thermal reactor, there is a spray system. So in your interaction in a European country, whether they are also putting this spray with the charge, means charge spray. So it will further enhance the aerosol, what we call the filtration by spray. Because in our country, they are doing only spray, but I have found some literature where the people are using the charge spray to create more fine particle or more homogeneous spray droplets.
Yes, I know this is the project that was PASAN, European project, and one of the project where they studied this. But what I can show you, Dr. Amit, this was the experimental level work. Means this was done by RSC in Italy and also by in Finland people I think were involved. But RSC Italy, and this was to see this different type of spray droplets where you can generate the finer drops to capture. But I am not aware about the real reactor application. At lab scale, it showed better efficiency due to the charging and also due to the small droplet, because small droplet means you have the high surface area.
Surface
This
area.
is clear. High surface area. And by high surface area, you capture more particles for sure. This is clear. Because larger bubbles or droplets will simply settle down in the containment. If you have the fine, really the drops, and this was, I think, ultraviolet or some they use by oscillations, I remember. But you generate the very fine droplets. But this was also one concept was also to do it by very high velocity injection. But again, objective was same, to generate as fine droplet as you can, because fine droplets will provide you higher surface area, and higher surface area has the better, let's say, the captivity efficiency.
Okay, thank you. Over to Mariam.
Okay, sir. So I think there are no more questions. So on behalf of everyone present, I would like to extend our heartfelt thanks to Dr. Sanjeev Gupta for delivering such an insightful and thought-provoking lecture. Your expertise on the subject has enriched our understanding. A big thanks goes to ISTA team for organizing this lecture and creating platform for learning and knowledge exchange. I would also like to thank TESCON India for sponsoring this lecture. And finally, thank you to our wonderful audience for your participation, engagement, and thoughtful questions. Thank you all once again. Thank you.
Thank you very much from my side as well. Thank you very much for your
Yeah.
attention and goodbye.
Thank you. Thank you. Thank you, Dr.
Thank
Gupta.
you. Welcome.
Thank you.
Well, my
Have a
pleasure.
wonderful-